Hi there, I am Dilya from ANU. I am a many-year PhD student. As we all know, research unfortunately can't be the entirety of our lives. It takes a bit longer for some of us. Anyways, I'm here to talk about the kinematic mass scaling relation that I have been doing with Sami and Shade. I will explain what Shade is later on. Oh, I do have control of your screen. So much power. All right, so essentially my research topic revolves around this generalized scaling relation where I try to combine Tyler-Fisher relation, as you can see on the left, Faber-Jackson relation in the middle, together to make a unified scaling relation that can work from early type galaxies to late type galaxies using this parameter called Sk, where k is typically 0.5, and we call it S05 scaling relation. So this is a work I did with Sami last year, and you can see it has the potential to reduce the scatter from both scaling relations, and it shows to be quite promising in being this one truly unified scaling relations. Now, if I go to the next screen. Now, the thing is, when we did that work, we realized there are some limits. So here I have the stellar version of the scaling relation on the left and the gas version of the scaling relation on the right. They're color-coded by their visual morphologies. One of the things that we found is that as you go down to lower and lower mass, we are starting to hit a wall. And now I call it the kinematic measurement limit because looking at two plots, the values were getting really close to the Sami spectral resolution limits. Now, on the left is about 60 kilometers per second. On the right is about 20 kilometers per second. So, we say, okay, what's happening here? Does that mean these small late-type spiral galaxies don't belong on the scaling relation? Does that mean for this unified scaling relation, I actually need to exclude some of them? So, but the thing is, I set out this work to bring them all together. It would be kind of wrong for me to say these don't belong together, so I'm just going to exclude them. Then I can no longer call them unified scaling relations. So in the hope to figure out what is wrong with them or what makes them special, I decided to pay closer attention to them. So what we did is, well, we got very lucky. Australia decided to join ESO, and we got time on VLT. So we used Flame Argus IFU instrument to look at dwarf galaxies because we use this instrument because it has very high spectral resolution where you can see the spectral resolution limit is at about 9 kilometers per second. And now the catch is that we don't have a lot of wavelength coverage. So that means I have to be very specific about what I look at. So we decided to focus on H-alpha kinematics for these really dwarf galaxies. And we're looking at 10 to the about 6 to 10 to the 11 solar mass galaxies. And we observed about 70 of them. Now, so the thing is, we look at these very small galaxies so that, that means that when we look at these very special cases, we need to adjust our eyes, really. So that's what Shade is about. So you can see it's a survey of H-alpha from dwarf emissions. So here we have the SDSS image and H-alpha image on the right, velocity map and velocity dispersion map. Now these plots are not as pretty looking and smooth as we have with Sami. Sami has a huge team behind it, and so much thanks to everyone that worked so hard on it to get to that stage. If you haven't got a chance to look at Sami IFU data cubes, I highly recommend you have a look at them. A lot of them are just very pleasant to look at. Anyways, so with Shade, we have the advantage that I have there is that really high spectral resolution limit, which is really what I'm after. And you can see the velocity, the mass distribution in the bottom left. So essentially now, I plot them again. I plot those three scaling relations again. So here you can see the blue galaxies are SAMI galaxies, the red ones are shade galaxies, and the stars are overlap. So shade actually does follow up SAMI for about 20 galaxies or so. So with that, we can have an idea of if there is a systematic offset or not, just as a control sample, really. And what we found here is that, okay, it seems like, you know, dwarf galaxies really don't fit on these scaling relations. These scaling relations don't apply. So they're not as universal as we thought they were. So which was a very pity experience for me. I had a look at the rotation velocity, the Taylor-Fisher relation for dwarf galaxy, and they don't seem very out of the ordinary. And so really, spectral, so the velocity dispersion limit here in the middle that we can see is really what is causing this flaw. And the vertical line in the middle panel is the spectral resolution limit. And you can see the S05 relation is still hitting that wall. So now I have a choice to say, okay, these galaxies just don't belong here. Or I can say, okay, what is missing? What am I missing? So essentially, with these galaxies, I look at, what I know is that, you know, dwarf galaxies, when you go lower and lower in the stellar mass, you have more and more gas. Now, the whole time I was looking at stellar mass, I was ignoring the gas mass, so it's unfair. Thank you. Yes, sir. I saw that. So, yeah, so it's unfair for these galaxies if I just going to ignore their gas content. So what I did was a crude estimation using the star formation law to estimate what their gas density is and estimated their baryonic mass, really. And when I do this, what happens is that you can see the scatter or the bend, really the extent of the mass distribution in dwarf galaxies has shrunk. There's greater overlap. There's a bit less bend in the scaling relation, but you can also kind of see now we are getting a bit more bend on the high mass galaxies. So it means that it would be, it means that, you know, we are still missing a little bit of thing. There's still a bend. All right, what else how far can we stretch this? So, okay, keyboard doesn't work. So, no spoiler. So, you know, if we can look at, if we can have a more holistic view of things, if we not only look at stellar mass, baryonic mass, what if we look at the environment they're in? I mean, by that, I mean the halo mass, the dark matter halo around it. Now, here's a paper, a graph and a formula from Moster et al. 2010, where they use stellar mass to baryonic, stellar mass to halo mass relation for very massive galaxies. Now, I'm going to do a switcheroo here, essentially say, okay, these are very high stellar mass galaxies, and they're mostly stellar mass dominated as opposed to gas dominated. But if I treat this stellar mass to halo mass ratio as a baryonic mass to halo mass ratio, I know it's a bit hand wavy, but just stick with me here. That means that I can use baryonic mass to halo mass ratio to calculate the halo mass. Well, really, to crudely estimate it. And that's what I get. So now this scaling relation is much straighter. Granted, there are a lot of scatter because I did a lot of assumptions and did a lot of estimations, but, you know, when you consider everything, you know, they all kind of come together. So really what I learned from this very scientific approach, scientific experiment is that, yeah, so, you know, galaxies, they can come together. And I think there's something about that we can learn about it. Thank you.
All right, thank you, Dilya, and may I say an excellent use of using headings within your slides. Let's have a look at the Q&A. I think there were a few, but they disappear from my screen, so maybe they were answered in between. I don't see any. Oh, I think there's a new one. So there's a question from Adam Watts. Is it possible for the H-alpha kinematics for the low mass systems that they're not tracing the flat part of the rotation curve, therefore underestimating the true rotational velocity?
Yes, that is a good question and very straight to the point. Indeed, we are looking at 1RE. So for a lot of galaxies, we are not really reaching the peak of the rotation curve here. So, that could actually explain, that could be an effect that, okay, I lost control of the screen. So if you remember, the rotation velocity is somewhat fine, whereas we're really limited by the sigma floor. So if we do go up, in rotation velocity, in bigger radius, yes, the rotation velocity will increase, but then it really depends on how far or how fast they increase in comparison to early type galaxy and late type galaxies. Because otherwise, if they all just shift the same amount, I still have the floor, it'll just be shifted the same amount. So the assumption is that if early type galaxies, when you go larger radius, can increase rotation velocity much more than dwarf galaxies, then yes, you can potentially straighten it out. But unfortunately, we don't have data extending that far. The Jessica Bloom's paper 2.2 RE, the slope what we can see is that yes, there is a bit of a shift, but unfortunately for smaller galaxies, lower mass galaxies, we don't have that data yet. But definitely, it is possible to fix the bend a little bit by going to larger distance, larger RE.